at Capstone, Water Quality Improvement for an Urban World, and our unit is called the Quality Water and Contamination Control Unit, also named as the QUAC. We are aqueducts, and my name is Vanessa Woolley, and this is Amir Samadami. We also had another partner, Sterling Knight, all working on this project, as well as contributions from Tao Kai and Rosalia Ataudue Ramirez during the inception of this project. Our advisor is Jeremy Bricker, and this is supported by the Engineering Honors Program, as well as the Center for Socially Engaged Design. So as an introduction to this, water quality is one of the most important factors for human health and well-being, and water quality is a super important issue, and it's growing even more important as cities grow and infrastructure ages. Climate change has also altered both the frequency and intensity of storms, putting additional burden on the already burdened systems. And this has been causing sewage overflows from combined sewage as well as just regular sewage areas that are not combined stormwater. And this results from insufficient capacity at treatment plants, and they have been increasing in frequency in some places. And this project started through the Innovation and Action Program of winter 2021. And we followed the socially engaged design process with the sustainability goals of life below water, clean water and sanitation, good health and well-being, reduced inequalities, and industry innovation and infrastructure. So just as an introduction to what we actually made, it is a contamination control unit that is put at the outlet pipe of the extra water that is being dumped from the system. So, and what we have here is, as you can see here, we have a catchment here. Water flows through a first screening, then through a turbine, and then through several filters and some UV. UV has been shown to be 99% effective within 6 inches of the UV in 10 seconds. And it is extremely effective for damaging the bacterial DNA and reducing virus load, which is a huge problem with water going into untreated water. And the initial design is once again shown below. I'm going to pass it on to Amir, who's going to talk about global and systems impact.
Thanks, Vanessa. Now, before we even designed the prototype, we initially set out to reach our goal that we would create a prototype that's also environmentally friendly and also is sustainable for the communities it serves. And as many of you guys know, that with the Flint water crisis, there's been a lot of distrust within our communities in Metro Detroit in particular, and water treatment in general. So we wanted to establish that not only are we creating a solution that would benefit the communities it serves, but it'd be reusable and sustainable too without harming the environment there. And one of these challenges was making it affordable for municipal counties to even be able to afford it. We had a budget of sub $1,000 so we could ensure that this prototype could be established and created effectively without spending a significant amount of money. And also additionally into that, that we wouldn't require significant skill or enormous amounts of technical agility to really create this prototype. A lot of workers who might not have the technical background will be able to create this prototype relatively easily and be able to effectively construct it without having too much physical labor or damage to their bodies. And in addition to that, one of the impactful benefits of our prototype includes that it is biodegradable in terms of the activated carbon that's used, and it lasts about 3 to 3.5 years, to about 36 months-ish before it has to be replaced, but there are no negative externalities created by that. That was a huge impact right there. And while we were actually designing it, we determined that the optimal shape for a prototype would actually be more cylindrical as opposed to having a more concrete, boxy, square shape, as the amount of volume that would be concentrated in that area would not only prevent to actually fit this in many sewage municipal department areas, but it also would cost more money and would not exactly be ideal in terms of water flow rates going right through. And I'm going to briefly pass it back to Vanessa, who's going to introduce us to the methods.
So throughout this semester, we have been testing and constructing our prototype, our initial prototype. And so just talking about some of the testing we did. So we were fortunate enough to be given a Sechi disc to borrow from Karen Aloss in the C department, as well as using the Flume Lab and EWRE, and we'd like to thank Jeremy Bricker and Aline Cotel for letting us use that. We conducted that on April 2nd, 2022, and we put water with varying turbidity throughout the model, and the turbidity was measured before and after to get a comparison. Turbidity was measured with the Sechi disc, and then we have a turbidity to depth equation up here, but we did this, and that's something that we can talk more about if you would like to. And multiple trials were performed to conduct statistical analysis varying flow rate, though we would like to have done more trials. And I'm passing this back over to Amir.
I'm kind of getting into like the nitty-gritty part of the actual model of statistical hypothesis we conducted. Our big research question that we really want to establish is that whether or not we want to identify there's significant turbidity percentage reduction accuracy at a given flow rate that we were testing. And we decided to test two flow rates, a medium flow rate, which is about 1.69 gallons per minute, and a higher flow rate at 3.69 gallons per minute. And as we mentioned before, the dependent variable was indeed the turbidity reduction percentage. And we really wanted to identify whether or not there's a significant accuracy in our prediction about how much turbidity was actually reduced at that percentage. And the ideal would be about 40%, and we want to make sure that was consistent. And throughout our data, we determined that, before we actually get into that, we determined that our t-set statistic was an alpha rating at 0.05. We had normal conditions established. And basically getting into the math of it, we had, as you can see here on the far hand side, we had 3 trials per each flow rate, and the turbidity percentages are listed above there. And in results, we decided to conduct a single sample t-test for both different flow rates, as they're both independent samples, as we determined. And we got into it by determining that we got 3 trials. As you can see here, these are the listed values of percentage reductions. We calculated the averages or variances, and we did some math and got the t-statistic here. And basically how a single t-test goes is that if the t-critical value, which was determined from a table or through computer methods, is greater than our null hypothesis, which is with ideal condition about 40% reduction, then we fail to reject that hypothesis, and we determine that there is no significance in the data in terms of having an accurate percentage reduction consistently throughout every trial. As you guys can see here, our data, we only had 3 samples per flow rate, and the t-critical value in both scenarios was actually greater than the t statistic that we calculated. And that basically shows that we didn't significantly have any correlations, nor did we have significant accuracy consistently throughout those 3 trials. So we failed to reject the null hypothesis. However, this is not necessarily a bad thing, as this is a prototype and we were actually aiming to improve upon this. So it's actually a good thing that we identified areas at which we failed our t-statistic and the null hypothesis was failed, as we can further optimize our prototype by actually changing potentially of the layouts, the materials that are being used, and basically seeing where in what flow rates are the upper bounds and the lower bounds of where it's actually significant, and we can adjust our prototype accordingly. And I'm going to pass it back to Vanessa, who's going to wrap things up for us.
So as you can see from this, we have just demonstrated by testing that our design has the capabilities to reduce turbidity around 40% throughout our testing. However, it was identified that there is no significant accuracy in our t-testing at both medium and high flow rates. Though, as we talked about in the introduction, the UV will reduce the bacterial load by about 99% as we hope, which is a huge reduction as opposed to that full bacterial load going into the system. And then the next steps include design improvements and further testing. So further testing would be more flow rates, more turbidity, just more in general, as well as larger and smaller flow rates. And improvements to the design that we would like to include are adding solar to make this energy independent, adding a turbine to do the same thing, and then scaling up to a furrow size model, as well as the outlet, we would like to shift it down. So instead of being in the center, it is at the bottom, so there's less stagnation as it flows through. And then we'd like to acknowledge Tao Kai, Rosalia Antadwe Ramirez, Jeremy Bricker, Aline Kotel, Karen Alofs, Tai Sang Kim, Kathleen Puebedox, and the University of Michigan Center for Socially Engaged Design, with special thanks to Aaron Moore, as well as the University of Michigan Engineering Honors Program and the Penn State University College of Agricultural Studies for their contributions to this project.